Welcome to this Ophir Photonics webinar. My name is Mark Slutzki, Product Manager for Power Energy Measurement Solutions here at Ophir, and thanks for joining us today. I have to say that this is absolutely one of my favorite topics. We did a webinar on a related aspect of laser-based medical applications about 1.5 years ago, together with photonic spectra. So if any of you attended that webinar, you might hopefully find that some of the concepts we're going to talk about may sound a little bit familiar. I'm assuming, okay, why isn't this working? Okay, another glitch it seems. Okay, again, I apologize for this technical issue here. Okay, let's see if this works. Okay, now we've got some movement here. Okay, again, I apologize. Until a few months ago, we were using a different platform for webinars. We switched over to this platform, GoToWebinar, which is excellent, but I'm still learning the ropes with it here. I'm assuming you're at least somewhat familiar with Ophir. We have, after all, been doing this stuff for well over 40 years. Basically, if I can summarize what it says on this slide, we like to do the hard stuff that you'd be very happy to get off your head so you can focus on your work and not have to lose any sleep worrying about the tools you'll need to help you get your work done. Okay, I think that's a pretty fair summary. Okay. January 19th, 2006, NASA launched a space probe called New Horizons to explore what was then still called the planet Pluto. Poor Pluto had no idea that within a few months it would be demoted from planet to dwarf planet. There are still arguments going on about that to this very day among the astronomical community. Living where I live, I can only envy people who that's what they have to worry about in life, but okay. So it was launched January 19th, 2006. Just over a year later, February 28th, 2007, New Horizons passed by the planet Jupiter at just such an angle, just such a distance, just such a velocity that Jupiter's huge gravity flung the spacecraft in a new direction, carefully calculated to bring it to this point in Pluto's orbit at exactly the same time that Pluto would reach that point in its orbit. That gravity assist also increased the spacecraft's velocity by something like an additional 4 kilometers per second. Don't worry, no laws of physics were violated. Jupiter lost the same momentum that New Horizons gained, but because of the difference in mass between the planet Jupiter and the New Horizons spacecraft, Jupiter's velocity was reduced by something like 10 to the negative 21 kilometers per hour. I realized that this animation is not actually from New Horizons, but it was the best animation of a gravity assist that I could find. New Horizons arrived at Pluto on January 14th, 2015. If we want to be pedantic, at exactly 11:49 UTC. At the moment of closest approach, it flew just 12,500 kilometers above Pluto's surface. So we had 9.5 years of flight, covering something like 5 billion kilometers and on a complicated trajectory, not exactly a straight line. And now hold on to your seats. The moment of arrival took place within less than 1 minute of the time that had been calculated during the planning all those years earlier. Within less than 1 minute. Okay, that's pretty amazing. Science and technology work because they're based on numbers. And those numbers come at the end of the day from accurate measurements. Now we know why I started off with this. So here's what I'd like to talk about today. We're gonna obviously as the title says, we're going to be talking about keeping good, tight control of laser-based medical applications. So we're going to look at medical and aesthetic applications of lasers, focusing on monitoring laser performance to keep the process doing what it's supposed to be doing. Remembering that the title of this webinar includes the words how to get it right, we're going to map out the thought process used to identify and configure the appropriate monitoring and measuring solution and the most intelligent way, the most intelligent approach to implement it. As we'll see, it's usually not trivial. Now, I should point out that this algorithm we're going to look at is actually a model. The same algorithm will work in any other application, with only the technical details that would be translated. After all, laser cutting in automotive manufacture or additive manufacturing, via hole drilling in semiconductor wafers, PV dicing, from the perspective of monitoring the laser to make sure that the process stays on track, there's no real difference between these. I'm going to want to spend just a minute or two talking about a common mistake that's made by laser-based medical system designers, integrators. It's almost a side point, but it's not. I'll just say that it's sufficiently common and sufficiently mistake that I thought it would be a good idea just to put it on the table. Then we'll look at some applications and some specific case studies. Truth be told, I'll actually be throwing in a few interesting case studies here and there throughout our discussion where they'll be specifically relevant to what we're talking about. And then we'll close up with a few concluding thoughts where I'll explain why I said what I said about this being one of my absolute favorite topics. And those last 3 or 4 minutes are actually my favorite part of this whole discussion of the topic when we get there. So let's begin with an overview of medical and aesthetic laser applications. In general terms, we can divide laser-based medical applications into 2 groups. One is where the laser beam itself is the actual treatment tool. Basically, we use the laser beam to zap tissue, and the differences come down to the details of what type of tissue and what type of zapping. Cutting into heart muscle or doing a dental procedure or performing corrective eye surgery, obviously we're going to be using very different levels of brute force. By the way, I forgot to just mention a few logistical notes. The total time of today's webinar should be approximately 50 to 55 minutes. Questions, comments are welcome using the text chat that you see in your panel there. I'm not looking at it full time because it takes up like half of my screen, but I will look at it every now and then. So if you have any questions or comments, please do post them, and at suitable points in the flow of the information, I'll hopefully remember to stop myself from talking, which is something that I like doing, the talking, not the stopping myself. And I'll check for questions, comments. I will also mention that I'm going to leave my contact information up on the final slide for a minute or so after we're done. In case you want to contact me offline with any questions, comments, you're more than welcome to do that. Now, from these details of what type of tissue and what type of zapping, we're going to derive the wavelength that we're going to use and the power levels and whether we're using a pulse beam or a CW beam and the delivery method and so on and so on. A second way that lasers fit into medical applications is by being used as a production tool for the manufacture of medical devices such as this stent or a pacemaker, or devices for controlled release of a drug or something like that. There's a whole industry based on aesthetic treatments. By aesthetic, I mean a procedure, excuse me, whose primary purpose is to improve appearance rather than function. We'll look at some important issues with aesthetic laser applications in a few minutes. For now, though, I just want to ask, what's the difference whether I define an application as medical or aesthetic but not medical? So that brings us to the more general subject of regulatory issues. And I'm not even going to pretend to go into any detail with regular issues. It's a huge topic. And there are expert consultants out there who earn their living by helping medical device manufacturers make sure that their products comply with all the regulatory requirements so that they can get the product to market successfully. I'll just briefly mention that the degree to which the regulatory agencies will stick their nose into the production and marketing the life cycle of a particular product will depend on the degree and nature of risk that this product or process might pose to a potential patient. When it comes to lasers, the degree of risk is going to depend on such things as the power of the laser, of the beam, the power density, how many watts per square centimeter on that actually reach the patient, the time over which the patient is exposed to this beam, the wavelength, if it's a pulsed beam or CW, short pulses, long pulses, to what degree does the patient actually have access to the beam, a very high power beam, but that's safely contained within the panels of a system will presumably pose less risk. Still in our overview, the need to monitor the laser's behavior so that the medical process stays on track comes into play in all levels of the supply chain, from the development through production, through system integration, and all the way out to field service engineers' toolkit when they go around the world servicing the systems that have been installed. Each of these levels of the supply chain might have different particular needs, of course, and so they might use different tools, but the need itself is there. Okay, let's talk a little bit more, I guess we'd call it meat and potatoes, about going about defining the best monitoring solution for a given application. So I like to do this in as clear and systematic an approach as possible. So step 1A, and this is unquestionably the most critical step, and you'd be surprised at how often even seasoned professionals kind of might miss this. And that's defining what parameter I want to measure. Okay, I understand that I need to measure my laser, whatever that means, so that my laser-based process will do what it's supposed to do. In medical applications, very often I might even be required by law to do so. But okay, what does it mean to measure my laser? Do I want to measure the weight of, so what we need to do is we need to identify the key parameter or parameters that actually make my process happen. Those are the ones whose details I want to keep track of, because unwanted changes in those parameters will have can potentially have negative effects on what my process is doing. Those are the ones that we're going to want to monitor. So just to illustrate this, let's look at some specific and pretty typical non-medical application examples. So I'm going to talk about industrial applications like laser cutting, drilling. What generally makes that process happen is the number of kilowatts per square centimeter that are hitting my target material. That's what's going to determine if and whether and how I'm going to be zapping that material, meaning cutting it, drilling it, whatever it may be. Also, the beam shape is going to have an effect, because it's going to affect the focusability, if I can invent such a word, and also of the beam, and also it's going to affect, intuitively, it's pretty obvious, the shape of the final spot inside of which the work is going to happen. That could make all the difference between a good cut and a bad cut, between scrap parts and good parts. We very often might prefer, rather than directly measuring power density, there are tools that do that, but it's usually easier to just measure the power, and we're going to absolutely want to do that outside the focal plane. We don't want to measure inside the focus if we don't have to, because it's the same number of watts or joules or whatever outside focus as inside focus, but inside focus is where the power density is high enough to zap material, to cut, drill, melt, vaporize, and I could just as easily end up zapping my power measurement instrument, and I don't want to do that. So very often it's easier to measure just the power outside the focus, And assuming that we know exactly what the beam shape and size inside the focal spot will be, and that's a big assumption, then measuring the total power alone outside the focus should give us enough information to tell us what we need to know. Welding is generally done using pulses. The parameter of interest there is most often going to be the energy density per pulse, and so on. Just a few other examples, military applications, shooting down a target, shooting down an incoming missile. Where I live, that's of some passing interest. So there, we're not normally going to be using a focused beam because it's not really very easy to bring a beam to a focus on a target that's a couple of kilometers away from me. So generally, we're going to use a beam of known diameter, and we're going to want to put in X number of kilowatts of power into that beam. And obviously, there's a whole bunch of other things that we'd have to do to make this application work. It has to be on the target for the right amount of time. The distance, the atmospheric conditions between the laser and the target, the shape and the material of the, okay, obviously lots and lots and lots of details. And another military application, couldn't resist adding this. If you recognize where that's from, you already know more or less how old I am. If the color of my beard didn't kind of give that away. All right, so here's an interesting case study. This is from a couple years back. It's on our website, actually. Medical device manufacturer, customer, they, among other things, they make this implantable device. I have no clue what this device is or does, but it includes in its production process a critical weld. Now, they were producing this component in parallel at two different facilities of theirs with a laser welding setup. The two setups were supposed to be exactly the same equipment, same setup, same everything, same process, except that the welds coming out of one facility were good and welds coming out of the other facility kept on failing. Luckily, not inside a patient, but at inspection. And they couldn't figure out why. They asked us to help diagnose the problem. So indeed, the equipment for the laser welding was the same. The setup was the same. The processes looked the same. When we started analyzing the beam profile, the spatial distribution of power in the beam cross-section, turned out that something was not exactly the same. It turned out that some element of the beam delivery optics in the second facility from which the welds kept coming out bad had shifted out of alignment. Once that was found, fixing it was relatively easy. So with a perfect vision that often characterizes hindsight, beam profile, it turns out, should have been part of the answer to step 1A, defining what parameters make the process happen or significantly affect how it happens. Step 1B, what time constant of unwanted drifts am I trying to catch? There's slow drifts and there's fast fluctuations, two entirely unrelated, usually, issues. Now, these two steps, 1A and 1B, are generally going to help me determine, first of all, what measurement technology I want to look for to implement, and also it'll help guide the choice of implementation. At what time intervals do I want to measure? So, for example, there's a painfully well-known effect with laser diodes called degradation. There's two types of that degradation that can affect laser diodes. One is wear out, as it's called. It's a gradual degradation in the quality of the laser diode and the quality of the beam that it's producing. That's caused by things like the slow or relatively slow growth of defects in the crystal, oxidation on the facets of the diode, electrode degradation due to metal diffusion from the electrode into the crystal, and so on. There's also random degradation, which is basically sudden laser diode death. When I was a student in my third year, we had a third-year project, and a friend and I were doing a project that involved laser diodes. This was in the early 80s, mid 80s. laser diodes were still kind of new, and we had a whole batch of laser diodes that we were working with, and they just kept on dying on us one after another. Turns out that the ESD, the electrostatic discharge from my fingers touching the diode itself, or even touching the mount on which the circuit board was being held on which the laser diode was mounted, was enough to introduce enough of a warping to the diode that the facets were no longer parallel, and it stopped being an expensive laser diode and turned into just a cheap photo diode, a cheap LED, basically. Step 2, where do I want to measure? Sounds like a trivial question. I could measure external to my system at the target location. I could measure inside my system, for example, sampling a few percent off the beam as it comes out of the laser and keeping track of that. So here's one possible implementation. I have my beam going off to the target. Wait, let me here, my little spot, my little laser pointer, virtual laser pointer. And periodically, once an hour, once a month, once a whatever, I move a mirror into the beam path, which deflects the beam into my power meter. I take a measurement, then I move the mirror out of the way and continue working. That's one possibility. All right, I'm going to get rid of that drawing because it seems to affect, here we are. Monitoring inside the laser, I could sample 0.5%, 2% of my laser beam continuously into a power meter. If it's a gas laser, I might take that coming out of the rear mirror leakage, or put a small beam splitter at the laser output, whatever it is. And there I'm monitoring continuously. So how do I decide? So there's a bunch of considerations here. If we first consider the internal sampling of the beam as it comes out of the laser, or more or less. So first of all, because I'm only measuring a small percentage of the full power of the beam, I can use a smaller, meaning cheaper, low power sensor. A small sensor often will mean a faster response time, which could be a big plus if I want to use my monitoring to provide fast feedback control to the laser driver. It means I can measure constantly. I'm not interrupting my process when I'm measuring, so I can, have a continuous monitoring. On the other hand, there's a downside, and that is that I'm only going to catch unwanted changes that happen near the laser. But if something goes wrong downstream, for example, something in the delivery optics shifting out of alignment, as we saw in that case study, I'm not going to catch that if I'm only watching the beam right next to the laser. On the other hand, if I measure externally, let's say at or near my target plane, so that will pick up changes that happen anywhere in the optical chain because I'm looking at what's actually arriving at the target. But there's a downside. I'm exposed to the full beam power, which means I need a power measuring instrument that can handle that full beam power. In medical applications, that might be hundreds of milliwatts, it might be hundreds of watts. And it interrupts the process because I'm stopping the beam with my power measuring sensor or my energy measuring sensor. There is a solution that many of our customers have adopted over the years that combines the best of both worlds, and that's what you see here. This is a side panel of a laser-based medical system, and there's an opening in the side panel called the calibration port. Inside that is a fully calibrated full power sensor. And periodically, either before each procedure or once a day or whatever it may be, depending on, the doctor will take the handpiece of the laser system, stick it into the cal port, fire the laser. The system will look at the readout that it's getting from that sensor, compare it to the power or energy or whatever that it was expecting based on the electrical set and the software settings inside the system. And if needed, it'll automatically make its own internal adjustments. And then the rest of the time, a small photodiode perhaps might be monitoring the power near the laser just to catch small changes, during the course of the procedure. As a side note, where in relation to the focal plane. Everyone knows, or they should, to measure the power outside focus, as we just explained. What's less commonly known is that it's usually or often preferable to measure before the focus rather than after the focus, given the option. And that's because at the focal spot, depending on the power and the size of the focus, there are often losses caused by photoacoustic shockwave effects. Tell me that's not cool. Okay, step 3, how? How do I implement it? So for example, if I need to catch fast changes, or if I want the monitoring to be fully automated without needing a human operator, the sensor might have a direct interface to the onboard controller, let's say by using RS-232 or USB or Ethernet communication, and its readings of power could be used to provide feedback control so that fluctuations in laser power can be automatically corrected. Alternatively, in some applications where the expected unwanted drifts in critical laser parameters are much slower, it might be enough for a human operator to simply place a handheld standalone power meter into the beam once a day, for example, just to verify that the power is within go, no-go limits, or once every X time to have the system automatically self-calibrate its laser drive. A specific but very common answer to steps 2 and 3 is to use a custom designed or custom modified OEM sensor built into the system. Laser-based surgical systems, for example, generally have a regulatory requirements to have an integrated measurement capability. The huge plus of this is that it gives you exactly what you need. It would be configured exactly for this system, for that laser power, wavelength, et cetera, et cetera, et cetera. On the other hand, because we're talking about at least some degree of customization, it would only make commercial sense if there's going to be some kind of a series production. This wouldn't make sense neither for the user or for the supplier if it's only going to be, a one-off or something like that. If we do choose to go the route of an integrated power measurement capability, depending on the specific needs of the application and its nature, there are lots of choices that would then need to be made, lots of different levels of integration, from using just a raw sensor element. In some cases, if we're talking about large quantities and advanced users, yes, there are customers who use that approach, just a raw, let's say a raw thermal disk, possibly with the measured raw analog sensitivity provided by us or the supplier. That would be its calibration. Moving up to detector elements with internal, external electronics, all the way up to complete sensors with built-in electronics, mechanical configurations, what have you. So here you just see a few examples of different OEM sensors that we've provided over the years. Sometimes there are special requirements that really need something designed from the ground up. So here's as an example, this is really one of my favorite solutions that we at Ophir provided over the years. In this particular case, large manufacturer of all sorts of very sophisticated medical devices. In this particular case, the beam was being emitted by a fiber radiator, but instead of the beam coming out of the tip of the fiber, as is usually the case in, let's say, telecom applications or something like that, I'm going to try my laser pointer again. In this case, it's a laparoscopic application, and the last couple of centimeters of the fiber length were roughened, so the light is being emitted in a cylindrical radiating pattern out of those last few centimeters of fiber. When this first came in, I was scratching my head. Okay, how are we going to measure this? I mean, I guess you could use a really big integrating sphere, but there must be a more elegant way. So what we eventually came up with, very slick, is what I like to call an integrating cylinder. Okay, basically we have a cylinder, the inside of which is the sensor. and the fiber is inserted inside a customer provided glass cuvette, which exactly fits into an opening at the end of the cylinder. Quick measurement, couple seconds, and then we're good. And the doctor can do that before beginning each procedure. The customer themselves, they were so excited by this, they showed this off at a couple of their professional trade shows. Lots of really nice ongoing business, if I may say so, with that one. This was a very cool one. Here's another example, another case study, and this is interestingly one that we did not end up doing. And I want to explain why, because I think there's an instructive and helpful takeaway here. Again, manufacturer of a range of different medical devices. In this particular case, at one of their facilities, they have a whole bunch of laser welding stations that perform a critical welding step on, as part of the manufacture of one of their devices. And they wanted to have the capability of measuring the energy of every single pulse emitted by every one of the lasers at all these laser welding stations and storing them in a central database, obviously for traceability purposes. Now, I understand the customer's desire to outsource this. It was, after all, really not in their focus. Pardon the pun, not really intended. Now, the measuring part of the solution is pretty straightforward. What you do is you attach a permanent beam splitter there that sends X% of the laser energy, each pulse, into a sensor, and you collect the readings from each of the sensors at all of the welding stations and collect them into a central database. However, our focus as a provider of measurement solutions is really only in this module. Just like the rest, the database and all the other stuff wasn't in their focus, it really wasn't in ours either. And we ended up deciding not to do this one. The takeaway here, I believe, is that wherever possible, the system designer should generally be the prime contractor, because they're the ones who best know everything that there is to know about the system. Okay, as I mentioned, I wanted to spend a minute pointing out a very common mistake that's made, if I may say so, and I hope nobody out there gets angry at me. This is quite typical of startups. And the more quickly the startup makes it and starts growing, the more quickly they learn that this is a mistake. And that mistake is, well, okay, I understand that I need to monitor the behavior of my laser so that my laser-based medical system, process, whatever, it continues to do exactly what it's supposed to do. Why don't I just put this together myself? I mean, I can buy a cheap photodiode from some online catalog for, I don't know, certainly less than $1. My engineers can easily put together an amplifier. What's the big deal? Why do I need to spend money on a calibrated, NIST traceable laser power meter, laser energy meter, or whatever it may be? So that sounds good, smaller costs on my bill of materials, on my BOM. My boss will be very pleased with me. But once we start getting into the nitty-gritty, then we start coming across a couple of issues. First of all, that's going to catch only changes that originate at the laser. Typical laser powers in medical applications, as I said, can be hundreds of milliwatts up to hundreds of watts. A raw photodiode will usually saturate at some fraction of a milliwatt, a couple hundred microwatts. So I'm going to need to add a whole lot of attenuation that's more than likely to introduce anomalies into the beam. I'm going to discover that, whoops, where's my, there's a dependence, that the photodiode's readout is going to have some kind of a dependence on the temperature, on the frequency, on the pulse repetition rate. If it's a pulse laser, I'm going to find that I've got significant variations from batch to batch when I start buying these photodiodes in quantity. In many applications, I'm actually going to need absolute accuracy that's traceable to some kind of a standard like NIST. Addressing these issues, they're addressable, but this is going to involve cost. Now, the cost might not show up on the BOM, but my engineers also cost, and every man day that's spent dealing with these issues is a man day, person day, that's not being spent on designing the products and getting them out the door. So that's kind of the point that I wanted to just take note of. Okay, so let's look at some common and uncommon but very cool medical laser-based applications, and we're going to see a few more case studies as well. When we think of laser-based medical applications, probably the first ones that come to mind involve surgery, CO2, YAG, some specialty type of lasers. CO2 is still the laser of choice in applications where the target tissue is very close to important non-target tissue. Including many laparoscopic procedures like gynecology. CO2 long wavelength, like 10.6 micrometers plus minus, has a very shallow absorption depth, meaning it's very readily absorbed by water, and our tissues are to a very large extent made of water. So that makes it easy to be highly specific and to minimize thermal risk to nearby tissues that I don't want to heat up, burn, cut, weld. Skin treatments often use laser beams to heat the area of skin where there's a problem, say sagging skin, wrinkles, things like that, and thereby stimulate growth of new tissue, which will be tighter and more aesthetic. Essentially, if you think about it, what we're talking about is a controlled skin injury, but one whose known healing process will bring the wanted results. Some skin treatments, tightening, resurfacing in particular, use something that's called fractional CO2. This uses an array of pulsed pixel dots rather than treating the entire area at once with a wide beam, so that the exposure is actually as a sort of a reticle of dots pulsing rapidly, and the whole array then scans over the treatment area. This method leaves microscopic columns of treated and untreated tissue throughout the treatment area. This was developed to shorten recovery time and reduce the risk of side effects. Measuring this could be a bit tricky, but it turns out that it can be done based on regular thermal type power sensors. The idea being that when I slightly defocus the beam, or even slightly defocus the beam, the individual dots will defocus by a relatively large factor, while the overall beam doesn't, so that it can still fit into the sensor's aperture, but each dot itself the power density there will be safely below the sensor's damage threshold. Some very cool applications dealing with eye treatments, ophthalmic laser surgery, excimer lasers, typically LASIK, I don't remember what that stands for, vision correction, avoiding the need for glasses. Typically we'll use excimer lasers, short wavelength UV lasers, 193 nanometers. The cool bit there is that it cuts tissue, not by burning it or zapping it, but rather because the energy of each individual photon, because the wavelength is short, the energy is high. Those of you who remember any modern physics courses that you might have taken. So even though we're potentially using relatively low power, but we're ripping molecules apart, not by heating them up, but by raising particular electrons up to high energy levels and breaking the bonds there, what's called photodisassociation. So we're not heating anything up, and so we're not risking causing thermal damage to surrounding tissue, and in the eye, that could be a pretty big deal. We just have to keep in mind that 193 nanometers also does pretty nasty things to other materials, including the sensors, potentially. So, there are some issues involved there. Lithotripsy, the idea is for treating things like kidney stones. In the 80s, in my late 80s, when I was still fresh out of my studies, early 90s even, I remember looking at some of these systems that they used to use what was called extracorporeal, meaning outside the body, shockwave lithotripsy. it looks kind of, you know, like a torture chamber, but the sedated patient would lie in a bath of water. Now, these kidney stones get lodged in tubes inside the body and cause blockages, and from what I've been told, pretty wicked pain. So what would happen is the sedated patient would be lying in a shallow bath of water, and the system would fire acoustic shock waves, mechanical shock waves, towards the person's kidneys. Now, these mechanical shock waves pass through the soft tissues of the body without doing anything, but when they hit the hard, brittle kidneys, they pulverize them into a powder, and the grains of powder are small enough that they can then pass out of the body through the normal channels through which stuff gets passed out of the body. Since the 80s, 90s, it's already generally done using lasers, a very minimally invasive laparoscopic procedure. Photodynamic therapy, this is incredibly cool stuff. The basic concept is that we can design drugs to a certain extent. It's constantly being extended, but we can design drugs that remain inert and inactive until they're exposed to a very specific wavelength of light at a very specific power and power density and total deposited energy, and only then they become activated. If you think of, God forbid, something like chemotherapy, these are drugs that are vicious chemicals. They kill cancer cells. They also kill healthy cells, except that they kill cancer cells better. So there's pretty wicked side effects that are often associated with the chemotherapy. Nowadays, together with the chemotherapy, there's a whole cocktail of medications that are given to minimize the side effects. To a large extent, that works. As you may detect on the way I'm talking, I'm intimately familiar with this. Unfortunately, one of our daughters is in the middle of going through this right now. Please God, it should be successful. If I don't even know to what extent photodynamic therapy has made its way into chemotherapy. I'm not completely up on things at the moment, but if you imagine a chemotherapy that would be designed for use as a photodynamic therapy treatment, the drug would be administered, it would make its way all over the patient's body, but it wouldn't do anything. And then in a minimally invasive laparoscopic procedure, a fiber would be inserted up to the tumor, illuminate the tumor, and only there it would activate the drug. It's an amazing, amazing idea. Very exciting concept. Lasers are often used in medical imaging. Here you can see a scan of a dental model, scanning the inside of the mouth to, you know, develop a computer-designed dental implant so it can be produced precisely to the right measurements. This is a relatively new one. I was just reading about this recently. Medical additive manufacturing of human tissue. So if you think of okay, we're not quite up to manufacturing organs yet, although there's a lot of work, incredible work going on there, but things like cranial implants, dental implants, things like that, that just boggles the mind. Dental in general, there's lots of dental applications that are based on lasers, cutting soft tissue, hard tissue, the two different regions of the gum. I just read about this a couple of weeks ago. Everybody's favorite, root canal. Okay, minimally invasive root canal. There's work going on, it's still in development, of using a laser rather than a mechanical tool to scrape and dig and scratch and pull out the stuff from the root canal that needs to be put out, and then flushing it out with chemicals to sterilize the inside so that infections don't develop after it's closed up. A laser of appropriate wavelength and power can do all of those steps in parallel in a couple of seconds of exposure, and then you seal the opening, and that's the end of it. Phenomenal, phenomenal. Everybody's probably aware of antibacterial and antiviral applications. UVC, particular wavelengths, I think 355 is, or 354 nanometers, I think is one of them, that are known to be able to kill bacteria and viruses. It's for many years been in quite common use in the food industry, sterilizing a work surface. A lot of work was done to deal with surfaces during the COVID-19 pandemic Remember that? There was such a thing once, right? Okay, we mentioned aesthetic applications. I said we would say a couple more things about it. IPL, intense pulse light, is very commonly used in aesthetic treatments, both medical and aesthetic only. Generally based on xenon flash lamps, generating flashes or pulses with energies typically in the tens of joules. I'm told that getting a pulse like that feels something like putting a tight rubber band around your arm, pulling it back and then snapping it. I'm told that that's what it feels like. They often have various interchangeable spectral filters to give a particular spectral profile that'll be as specific as possible in terms of the tissues that are affected. For example, destroying hair follicles or breaking apart molecules of tattoo pigment, different wavelength regimen. Also, the temporal profile, the pulse shape, the pulse on the time axis is often part of a specific design to give a particular behavior, such as depth of penetration into the skin and so on. Now, accurately measuring such broad spectrum, widely diverging beams can be very, very tricky. And at Ophir, we've developed some interesting tools to help us characterize some of the difficult parameters of IPL, such as this gadget you see here, the fishbowl as we call it, which we use for mapping the 3D angular distribution of an IPL source so that we can then quantify the accuracy of the subsequent energy measurements. Now, some IPLs, as I said, are yes considered medical, but those intended only for cosmetic treatments are generally not, which means they're not regulated. There have been efforts over the years to yes regulate IPL, basically because of the safety issues, but so far it hasn't happened. There seems to be a general attitude in the aesthetic treatments only industry that says that since it's not medical and not regulated, we don't really need to spend the money on measuring it. It is a tempting thought, but it doesn't always work out very well. I apologize for the unpleasant image, but this does need to be part of the thought process. Here you see some sensors that we have at Ophir that are specifically designed for IPL applications. Each of them use different optical tricks to fully capture and accurately measure the widely diverging beams that IPL systems generate. There are applications that are borderline medical, such as diagnostic instruments or some research areas. Research is cool because that's where we're going to find some of what will become tomorrow's medical treatment, things like flow cytometry, spatialomics. I read about this not long ago. This is the mapping of gene expression. All right, essentially, that means mapping of molecular level activities within a cell in 3D space throughout a given tissue. This allows studying the genetic basis and epigenetic mechanisms behind diseases. Genetic basis, for example, 25 years ago, amniocentesis could only identify genetic problems with a fetus with a resolution of entire chromosomes. Those are major and, at least back then, untreatable. Nowadays, though, we can spot problems with a resolution of individual genes, and many of those we can do something about. This can really revolutionize how we do medicine by paying attention to the root cause of a disease, its molecular, perhaps genetic basis, and not only to its symptoms. A few case studies, okay? And these are case studies involving our customers. We have these on our website. Obviously, we were given permission by the customers to mention them by name. We have to be very careful, obviously. So Asclepion Laser Technologies, major name in this area. Diode lasers, solid state lasers for systems for all sorts of different medical applications. These are, emit CW beams. They use a whole range of various thermal type sensors to measure the average power. They have many applications for which they have systems based on pulsed solid state lasers, and there they use pyroelectric energy sensors to measure the energy per pulse and the pulse-to-pulse stability. They even measure the pilot beams, the aiming beams that the doctor will use to aim the system before beginning the procedure. They don't miss a thing, okay? Very, very important. One of the points of pride for them is that they use the same sensors and the same measurement protocols all the way through the product life cycle, from the prototypes, engineering, all the way through series production, quality control, and even field service. It's very important to them to have maximum consistency all of measurement and therefore of performance all the way through a given solution's life cycle. In, I think, 2019, they introduced a family of picosecond lasers. And for those lasers, they found that the beam profile was another parameter that was critical. And so they learned that they need to keep track of that as well. And here's an example they shared with us of a set of 2D and 3D images of beams from a system that was where the optics were not properly aligned. And on the right side, you can see corresponding images of what the beams looked like after everything was properly aligned. The differences really speak for themselves. Another case study, Diamond Tech, another prominent name. They came out with a non-invasive blood glucose monitor for people with diabetes, so that they don't have to keep poking themselves and drawing drops of blood. For some people, it's no big deal. For some people, it's really unpleasant. Now, there have been many attempts over the years to develop non-invasive systems by measuring the glucose level in things like sweat, saliva, tears, but it turns out that the glucose level in those do not correlate very well with the blood glucose level, which is what we're interested in. It turns out that the level of glucose in the interstitial fluid, the fluid that our cells float in, that correlates well with the blood glucose level. So they use IR lasers, 8 to 11 micrometers, a technique to do with infrared spectroscopy. It's called photothermic deflection. Basically, the laser beam bounces off the person's skin, and I'm not going to go into the physics of what it does. Very, very slick stuff. But they found that in order for it to work, they have to quantify accurately a baseline of a whole bunch of different laser beam parameters, so that then when the measurement takes place, they can detect shifts from that baseline. So they need to measure the beam power, the pulse-to-pulse stability, the focal spot size, the divergence of the beam. So for the beam profiling aspects of this, they used to use classical knife edge profiling techniques in the R&D stage. That, okay, that's fine, but it takes hours to properly do one of those. Now they use an Ophir instrument called the pyrocam. Oh, there's I forget the word, rendition that they provide, that they have, I think, from their website of what it looks like. The pyrocam is a beam profiling camera where the imager is an array of pyroelectric detectors, pyroelectric pixels. And now, instead of taking hours to do a profile, it takes seconds. Here's an example that they gave us, a new laser that they were performing incoming testing and analysis on. They wanted to integrate it in their systems, and they measured all sorts of parameters of it. The engineers could not get the beam to focus properly. Studying the beam profile showed that the collimating optics in one of these collimating lens was out of alignment. Once that was found, the laser supplier was easily able to fix the problem. You can see what it looks like on the right after alignment. Everybody's happy. And faster measurements obviously mean a much more efficient development cycle. Okay, just a minute of concluding thoughts. And now I'm going to explain why I said that this was one of my favorite topics. First, and then I'll check for questions. I did not do so all the way through. Besides the fact that it was medical applications that first got Ophir Photonics started, expanding from just optics and coatings to photonics measurements, there's a sense of wonder in this subject that I personally find especially exciting. We discover so many wonders of the universe when we study the universe numerically in nitty-gritty detail and basing on accurately measured data. And as much as that's true looking outwards, galaxies, string theory, everything in between, it's no less so when we look inwards at ourselves. So I'll just give you an example. The human eye, is in a sense a camera with a resolution of 127 megapixels. Each eye has about 127 million detector elements, not all the same type, daytime, nighttime, okay? We would think, and each of them is constantly sending image data to the brain. So you would think that there should be, in the data cable, the data communications cable that connects the eye to the brain, you would think that there should be 127 million channels of data being transmitted in parallel to the brain. Turns out that if we look at the nerve cable that goes from the eye to the brain, there's not 127 million nerve channels. There's only about 100,000. So how does that work? So it turns out that there's an incredible signal processing system. There's a whole network of nerve connections at the feed out, if there's such a word, from the eye into the optic nerve cable that performs data compression. Unbelievable level of sophistication. It includes a few different components. There's image enhancement, for example, increasing contrast. Where a dark pixel meets a lighter pixel, our eye automatically makes the dark a little bit darker and the light a little bit lighter, just at the meeting point, to sharpen our sense of what we're looking at. There are lots of famous optical illusions based on that. If there were time, which there isn't, I would have shared some of them here. Now, this costs us some of the signal. We're investing some of the signal and some of the data back into the image processing. At lower light levels, our eye automatically adapts the amount of processing to the light levels so that we're only investing as much signal as we can afford to. Automatic gain control. Our eye can see over some 12 orders of magnitude. We have an auto ranging system in there. Our eye processes signals in time as well. That's how we can be looking at a dark scene at night, barely able to make out what's out there, but then a tiny movement out of the corner of our eye catches our attention. The data compression performed by that network of neurons takes care of all this. And the really amazing thing is that we're just born with this. Another example, and then we're going to conclude. The Human Genome Project was completed some years back. The goal was to map out and, as far as possible, understand how the production file works, how, to understand the instructions for producing us, or so we thought at least. Knowing what we know about all the various molecules that participate in the processes of life in our bodies, we expected to find at least 100,000 genes to explain all the things that, all the different molecules that are made using the instructions in those genes. Turns out there's only about 26,000. So again, there's an incredible system of data compression and data reuse, I guess we could call it, that's designed in. For example, there's a gene called PAX6, PAX6, that controls the formation of the human eye in a human embryo. I'm dreadfully oversimplifying things, I know. That same PAX6 gene in a fruit fly embryo controls the formation of a fruit fly eye. There's a whole suite of cellular machinery that controls how our genes control various processes, that controls gene expression. So we don't need as much gene data as one might have thought. Learning how to analyze and manipulate this epigenetic machinery opens potential doors to mind-boggling possibilities for treating and hopefully preventing disease, improving health, maintaining health as we age, health span as they call it, things we couldn't dream about until recently. It's been said that humans are merely a bunch of molecules, no different in principle from rocks or bacteria or intergalactic dust, naked apes, as one best-selling book title says. That may be true in terms of material structure, but these clumps of molecules are capable of asking questions and discovering how all those other clumps of molecules in the universe work and how to improve our existence by using that knowledge. How to improve not only our existence, but ourselves will require, I believe, other knowledge, or better, maybe wisdom of a different sort. I'm very highly optimistic. Okay, so in summary, we had an overview of some of the things that are unique to medical and aesthetic laser applications. We looked at the thought process of defining how we're going to implement a monitoring solution. We mentioned that very common mistake that's often made early on in a company's life cycle. We saw some example applications, a couple of interesting case studies, and the last 3 minutes of concluding thoughts, I think, are the main reason that I find this topic so interesting. Just to zoom in for a second on the thought process, we talked about which parameter, what time constant of unwanted drifts am I trying to catch, where am I going to measure, how am I going to implement, and what am I going to do with the measurements, and then sometimes there are special requirements. Thank you very much for joining us. Have a really nice rest of the day.